Hello everyone, we are moving to our last section in this class, section 8.3. We're going to talk about isomorphism. So here we are going to start with definition. You already know that we can have linear transformations, and those linear transformations can have special additional qualities of being one-to-one and being onto. So such transformation with both of these qualities is going to be called isomorphism. So for transformation to be isomorphism, it's supposed to be a linear, it's supposed to be one-to-one, and it's supposed to be onto. Well, the importance of isomorphism is going to be more clear after we prove next important theorem. Every real n-dimensional vector space V, so can have any kind of objects, important thing that it has n dimensions, is isomorphic to Rn, a vector space of n tuples, real number n tuples. What we will need to do, guys, here, we'll need to find a transformation and show that that transformation is onto and one-to-one. And if we do this, we are going to prove that the spaces are isomorphic, and that transformation is going to be called isomorphism. So my proof, I'm going to start with actually searching for such transformation. So let label set S with n vectors be a basis of that vector space V. And again, V can be any n-dimensional vector space. If it's a basis, we can represent any vector U which belongs to vector space V as a linear combination of basis vectors. Looks like it's missing the word. I'm going to write it down. So if it's a basis, we can represent any vector U which belongs to vector V as a linear combination with some constant C1 multiplied by V1 plus Cn multiplied by Vn. Let's create or define better. Let's define transformation T by the next rule. We take any vector U and just copy the constants in front of the basis vectors C1, Cn. So let's define transformation like this. So take any vector, represent it through the basis, copy the constants, and create a vector which belongs to Rn. And this one belongs to our vector space V, right? Basically, guys, we are going to use coordinates of a vector in a certain basis, and can be any basis. Now, we define this transformation. We need to show that 1, it is linear, 2, 1-to-1, 3 onto. That's what we're going to do. I'm going to do it step by step. So first one, transformation T is a linear transformation. So what we'll need to check? Homogeneity and additivity. So let's imagine I'm going to start with additivity. Let's imagine that we have two vectors, U, C1, V1 plus Cn, Vn, and vector V, I don't know, K1, V1, Kn, Vn. Well, just two arbitrary vectors which belong to vector space V. We can represent through the basis. Now, what is going to be transformation of the sum of them, u plus v. Well, if we add them together, we're going to have a transformation of c1 plus k1 v1, right? I'm adding the vectors and combining the coefficients of the same basis vector. v1 plus all cn plus kn vn. According to my transformation rule, it's going to be transformed into a vector c1 plus k1, c2 plus k2, and cn plus kn, right? Just according to my transformation rule, I'm just going to copy the coordinates. Now, what is going to be transformation of u? Transformation of u is c1, cn, right? Transformation of v, according to my rule, is k1, kn. So sum of these transformations, transformation of u plus transformation of v, is going to be just sum of the coordinates. c1, cn plus k1, sorry, not supposed to be a plus, supposed to be a comma, kn, and if you add them together, they're supposed to be added by the rules of vector space Rn, right? So we're just going to add them, and we're going to have c1 plus k1 and cn plus kn. And what we see over here, the sum is equal to this number. And actually transformation of the sum is equal to the very same number. So additivity is working. Homogeneity, B. Homogeneity. Well, again, I'm going to apply transformation to some vector u, and we are going to have c1, cn. And then I'm going to apply transformation to vector ku, where k is a scalar. I'm going to have, well, since I multiply k by all the components, I'm going to have k, c1, k, cn. Just how ku is going to be. Ku is going to look like k multiplied by c1 v1 plus cn vn. So basically, if I multiply it, I'm going to multiply it by every component, and I'm going to get the coordinates looking like this. So it's going to be equal to k, and multiplied, I can take k outside of each component, c1, cn, right? And this one is actually equal to tu. So k, tu. So we just proved that we can take outside the scalar, outside of the transformation. So homogeneity is proved. Okay. We are done with easy stuff. Homogeneity is proved, linear. So transformation is linear. I'm going to show that transformation is linear. Now we need to prove that it's onto. Number 2, T is not onto, 1-to-1. First 1-to-1. So 1-to-1 means that if two vectors u not equal to vector v, then transformation of u is not going to be equal to transformation of v. Well, how are we going to prove it? Well, if two vectors are not equal, then the coordinates of them supposed to be different at least somewhere, right? Because if you have, for example, vector u equals c1 v1, cn vn, and vector v, which is equal k1 v1, kn vn. Remember, somewhere when we were talking about basis and coordinates, we were saying that coordinates representation is unique. So if you do have two different vectors, you're supposed to have at least one different coordinate. Otherwise, it's going to be the same vector, because there is no two different coordinate representation for a same vector. It's supposed to be like either same vector or different coordinates. I'm going to write down at least one ci is not equal ki, at least one. I don't know, like maybe all of them are not equal, but at least one's supposed to be not equal. If all of them are equal, these two vectors are the same vector. And we don't need to deal with same vector, we need to deal with different vectors. If at least one of them is not equal, then T transformation of U is going to have, which consists out of C1, Cn, and transformation of V, which is going to consist of K1. Sorry, I'm trying to write down plus every time here. Kn is going to have at least one not equal coordinate, which means that they are not going to be equal because of the same reason. So transformation is 1 to 1. 1 to 1 was easy. Let me mark it here. Okay, and the last one, also going to be not very difficult, is going to be transformation onto. So T is on 2. What does it mean that transformation is on 2? Means that for every image we're supposed to have at least like one source. So if W, which is equal K1, Kn, then what is going to produce vector like this? Can we find image of what vector is this? Because this way we can show that it's onto, because we need to show that every vector in Rn, every vector W which belongs to Rn, is going to have some vector V which belongs to original vector space V. Well, I'm going to take these coordinates K1, Kn and create vector V, which is going to be K1, it's going to be K1 V1 plus Kn Vn. And V1 and Vn are going to be the bases, which we used in the beginning, bases. Well, since these are basis vectors and these are just like constants, this is a linear combination. Linear combination of basis vectors belongs to vector space V, just because actually all linear combinations are making up space V, which means that's going to be vector V. Then vector V also going to belong to space vector V, and means that this vector is going to produce actually W. So we prove that it's on 2. Well, I think we need to mark that we proved it somewhere in the beginning. Where is it? Not here, not here, not here, not here. What? We proved it's on 2. So we proved that T is isomorphism. T is isomorphism. So, well, kind of done with proving that isomorphism. Why isomorphisms are good? Well, guys, for Rn, a space of n tuples, we have a lot of theory and different theorems and how to deal with them, because we developed lots of stuff for them in chapters 1, in chapter 2, 3, and even 4. So if space of some other objects is going to be isomorphic to this Rn space, we can do stuff on Rn space and then kind of transfer our results to actually n-dimensional space, like any other objects. And that's very good because we have lots of like tools for Rn. I'm going to show you an example of isomorphism. Maybe a couple of examples of isomorphism. Okay, let's do example number 1. Natural from Pn minus 1 polynomials of degree less than n minus 1 to Rn. So let's consider polynomial degree n minus 1 is going to be a0 plus a1x plus an minus 1x to the power of n minus 1. We are going to have an coordinates here, right? So if we just use these coefficients as coordinates, that's going to create so-called natural isomorphism. Why we call it natural isomorphism? Because actually these coordinates are using bases which consist out of like vectors 1, x, x squared, and x to the power of n minus 1. That's our basis. And that's a standard basis. Okay. Maybe another example of isomorphism. Well, let's consider something with matches. It's example number 2. Question. Is TA from R3 to R3 isomorphism? Is matrix transformation with next matrix? Is this transformation going to be isomorphism? So basically, guys, we need to check 3 things. Linear, 1 to 1, 1 to. Well, how do we know it's linear? Well, we know that matrix transformations are linear transformations. So it's linear because it is a matrix transformation. Okay. Is it 1 to 1? Normally, guys, to check as 1 to 1, we need to calculate the kernel. But for matrix transformations, we remember that actually we can check if it has inverse. Because actually, what we need to check for matrix transformations, that homogeneous system is going to have only 0 solution. And it happens when determinant of A is not equal to 0. Because Ax equals 0 is kernel of TA is going to be only 0 vector when determinant is not equal to 0. Let's calculate the determinant. I'm going to use a last column to calculate the determinant. So plus, minus, plus, I'm going to expand by last column, plus, minus. So actually determinant is going to be minus 2, this element, others are zeros, by determinant of remaining matrix, which is going to be this and this, like, that's a determinant of remaining matrix, by determinant of 1, minus 1, 1, 1. Okay, minus 2, and 1 by 1 is 1, minus 1. So it's plus 1, because it's minus 1 and minus from determinant, so I'm going to have minus 4 not equal to 0. So kernel of T is going to be only 0 vector. Trivial solution. So we check this, we just need to check on 2. How do we check on 2? On 2 means that every vector of this space is going to have something from this space. We can find it. Well, let's just kind of maybe do it. Basically, guys, what we are going to do. So transformation Ax on 2. Let me do 1, 2. Is going to produce some vector b. This vector b belongs to R3, which is W, kind of. And this vector belongs to R3, which is our original space, V. So our goal is to show that for any like vector here from 3-dimensional space, we can find the vector which is producing it. Basically, guys, for us, it's going to mean that you can solve a linear system with, for every like right side vector non-homogeneous. It has a solution. How do we know that? The same fact that determinant is not equal to 0 is going to kind of give it to us, because when determinant is not equal to 0, determinant of A is not equal to 0, then we have A inverse. Oh, I'm going to apply inverse to this expression. So A inverse Ax equals A inverse B, right? These are going to be identity by x is x. So So guys, what we can say is that for any vector b, we can find actually this vector by multiplying it by inverse, which we know it exists because determinant is not equal to 0. And that's going to be the vector. So x will produce b. So if somebody gives you b, you will always find x which is producing that b. And that means that it's onto. So this transformation, this matrix transformation is isomorphism. We checked all kind of conditions. I put too many dots. Well, there are more examples in the book. My suggestion is to try them. Check whether something is isomorphism. Don't forget, guys, all three conditions are important to prove that something is isomorphism. Not only onto and one-to-one, onto and one-to-one. Also, transformation must be linear. If transformation is not linear, it's not going to be isomorphism. Okay, that's all about section 8.3, and see you in class.